Benford's law. This is a short video about a fun quirk regarding certain sets of numbers that can also be used by tax payment detectives to look for fraud. Let's do a quick thought experiment. Imagine a book showing the populations of countries of the world. Now imagine that we list all the population numbers we have in ascending order and take the first digit of every single number. We count how many times they all occur. You might think that there are an equal number of 1s, 2s, 3s, and so on in the first digit of these populations. However, if we plot the frequency with which these numbers occur, we get this shape. The lower valued first digits like 1, 2, and 3 occur with a much higher frequency, and as we move to the larger first digits like 8 and 9, the frequency decreases. It turns out that this happens a lot for certain sets of numbers. In 1881, an astronomer, Simon Newcomb, saw that a book of logarithm tables had well-used early pages, whereas later pages were not. He then wrote a short article in the American Journal of Mathematics, which contained the first digit law. Somehow, the law was named after physicist Frank Benford, who also came across it. How do we know that Benford's law has been satisfied? If the leading digit occurs with the following probability. The formula shows that the probability is the log to the base 10 of the digit plus 1 minus the log of the digit, simplified to become the log of 1 plus 1 over the digit, d. Filling in for digit 3, for example, we see that the probability of the first digit being 3 is 12.5%. Here is each digit and its respective probability. So we've seen that some sets of numbers follow Benford's law and not others. But does measurement unit matter? No, it doesn't. What's interesting about the law is that it occurs regardless of the unit of measurement. Following an example from Wikipedia, here is a table with a count and percentage of occurrence of the first digits for the heights of the 58 tallest structures in the world. We can see that Benford's law still holds and is therefore scale invariant. When does the law actually work? It works best when numbers include many different orders of magnitude in a uniform fashion. That is, numbers that are both very small, medium, large, and evenly spread. Good candidates are populations of villages, towns, cities, stock market prices, half-lives of radioactive substances, and eBay prices. Conversely, a list of the numbers that is mostly in one order of magnitude, things like heights or weights of people, their IQ scores, or time for completing a 100-meter sprint, are unlikely candidates for Benford's law. Then there are some sets that we think would follow the law, such as the prime numbers, as they do change magnitude as required, but they don't fit the bill. Why is any of this of use? Incredibly, things like tax fraud can often be detected using Benford's law, or the lack of its presence. Thanks for listening to this video. We're Micro Insights, a team of economists and data scientists trying to make sense of the world and find little insights where we can.